Hey, welcome back. The first 4 videos in this series introduced you to the idea of applying the derivative. Now, while we haven't yet looked at real-world examples in those overview videos, we should have some basic understanding regarding a curve's rate of change, its critical points, maximums and minimums, concavity, inflection, all of that good stuff. Now, this video is essentially some of my personal shortcut rules that I like to use, and as I always say, don't use my shortcut rules until you fully grasp the concept. Let's take a look at this curve, and let's try to analyze its concavity. So this is the curve of f of x equals 0.5 x squared, or half x squared. Now, we should know that it's always concave up because the slope of the tangent line is always increasing. So that means that the derivative of f is increasing, which means that the second derivative is always positive. And we should know that by now. But let me point out something very, very interesting. So let's go ahead and compare the tangent line of the curve of f with the actual curve itself. So let's go ahead and bring out that tangent line. There it is. So let's go ahead and see what happens, at the tangent line at each of these points. All right, there it is. It's going to go all the way through. Now, my question to you is, did we notice something in particular that could help us create some shortcut rule? Now remember, the curve is always concave up. We have stated that. Is it a coincidence, though, that the curve is concave up and the curve always lies above the tangent line? So let's take a look. You see here, the curve, here's the curve, and here's the tangent line. The curve is above the tangent line before and after that point. We're looking here and here. Yeah, it's above. We keep going. It's above. The curve is always above the tangent line. Now, is it a coincidence that the curve is also always concave up? That's the question that we're going to answer right now. In addition, let's go ahead and take a step back and look at that minimum value right here where we have that horizontal tangent line. Is it also a coincidence that we have a local minimum where the curve is concave up? Is it possible to have a local minimum if the curve is concave down? That's a question that we're going to answer in this video. And so let's take a look at another curve. We've seen this curve plenty of times. This is now f of x equals negative 0.5 x squared. We should be able to tell that this is concave down, but I'm using this as an example for further, more complex ones. So let's go ahead and take a look at that tangent line. All right. So if we were to observe, look, this tangent line at every point is above the curve. And I'm going to go ahead and reiterate that and say that the curve lies below the tangent line. The curve lies below its tangent line. And observe, this is concave down, the curve is concave down, and it lies below its tangent line. So here's my shortcut rule number 1. If a curve is concave down, its tangent line will lie above it. Or if we're just looking at tangent lines and we want to know about concavity, we can say that, hey, if the tangent line lies above a curve at any point or along an interval, then during that interval, that curve is concave down. That is exactly what I'm saying. We can look at the maximum value because it's still concave down at this point. We can look at any point to the left. We see that the curve is still below the tangent line. And over here on the right side, yeah, the curve is still below the tangent line. The tangent line is above the curve. So that's shortcut rule number 1. If the curve is concave down, the tangent line will lie above it. And conversely, and this is what you'll be using then, if you draw a tangent line and a tangent line lies above the curve, then the curve must be concave down. And again, this is assuming that we're dealing with a differentiable function along an interval. Now let's go ahead and continue solidifying that idea. So let's go ahead and take a look at this curve over here. This curve is the curve of f of x equals 2x cubed plus 2x squared minus 4x. So let's go ahead and pull out that tangent line right away. Let's take a look. Now on this interval, between -2 and what looks like somewhere here, it looks like it's concave down, and it sure enough is. Over here, it's somewhere, it's concave up from somewhere around here until infinity. And now, stating that, somewhere around here, quote unquote, that's not good practice at all. But for the sake of this video, I'm just showing you how a tangent line compared to the curve can assure you about its concavity. So I'm going to press that play button. Boom. Look at that. So the tangent line lied above the curve all the way from negative infinity all the way up until somewhere around here. We saw that now afterwards, the tangent line is below the curve, or the curve is above the tangent line. So here, the curve is above the tangent line, so we can assume that it's concave up because that holds true. Over here, the curve is below the tangent line, so it's concave down. Now what we want to know is, well, what's going on over here? Well, guess what? The point at which the curve's rate of change stops changing is a point of inflection. Look at this right here. This function is differentiable. We've already defined that. But somewhere over here, somewhere around, the slope stops changing. And I'll show you exactly what I mean. Let's start over here. Let's press that play button. Let's go ahead and slow it down a lot. Let's bring it back again and play it nice and slow. The slope of the tangent line definitely stopped changing, and then we see that the concavity did change after. So yes, somewhere around here is a point of inflection. Now we can definitely find that point of inflection by using the function. So if we have 2x cubed plus 2x squared minus 4x, go ahead and take a second, pause this video if you'd like, calculate the second derivative, set it equal to 0, and tell me if the curve changes concavity before and after, or the sign of the second derivative changes from before and after. And guess what? Even if you're lazy enough, that's fine. Let's go ahead and take a look at the second derivative. And here it is. This is the second derivative. The second derivative is f double prime of x equals 12x plus 4. Now, the 0 lies right around here. And that is negative 1/3. Negative 1/3. Negative 1/3, well, if we look at negative 1/3, that is right around here. And that is exactly where we found that point of inflection. Because we can see the second derivative is negative to the left of negative 1/3 and positive after negative 1/3. So yes, that would be a point of inflection. So I hope we can see that we can definitely calculate points of inflection, more precisely by using the function itself. But when it comes to identifying concavity along an interval, if we were asked to do it on a graph, which you most likely will, you should be able to definitely do that by simply using that tangent line. Because using that tangent line, yeah, look, if the curve lies below the tangent line, then guess what? The function is concave down during that interval. Another cool thing that we want to pinpoint here as well, take a look at right here, this maximum value. Whatever this maximum value is, notice, if it's a maximum value, to the left and the right, the curve has to be decreasing afterwards, before and after. And this is because it's a maximum value. It can't be a maximum value and have a value greater than it right next to it. That wouldn't make sense. For it to be a maximum value, that means the values to the left and the right are not as great as that value, as that maximum. And so yes, no matter what, if you draw a tangent line and the function's at a maximum, if this function is differentiable, then yeah, this function is concave down during that interval. Similarly, if we're looking at a minimum, look, the curve always lies above the tangent line at a minimum. And that's because the curve has to increase to the left and the right of that point. So yes, if we're looking at a minimum, the curve has to be concave up. Now, when it comes to looking at those points of inflection, it's hard to tell precisely where it is because it looks like it's going through an interval where it's pretty still. And that's completely fine. We can use more precise techniques for that. But when we're identifying a graph and looking at maxes and mins, we know about the concavity now just fine. And that's it. This video is all about being able to use that tangent line to better our understanding of concavity and maxes and mins. So in short, if we're looking at a curve that's differentiable along any interval, if we are looking at a maximum value, the curve is concave down along that interval. If we're looking at a minimum value, a local minimum or an absolute minimum, the curve is concave up. Next, if we're looking at the tangent line and the tangent line lies above the curve, or if the curve lies below the tangent line, this is the way I like to say it. If the curve lies below the tangent line, then the curve is concave down. If the curve lies above the tangent line, then the curve is concave up along that interval. We weren't able to precisely, use a shortcut rule to identify points of inflection, but we know what a point of inflection looks like, and we know what area it'll be in. So, until next time, keep watching and practicing and mastering. Next video, we'll be going over the relationships between f, f prime, and f double prime on a more technical level. And then afterwards, we're going to keep building that knowledge and start using algebra. So, until next time, guys, I'll see you.